Hi guys, this is Mr. Mellor. We're going to go over series and parallel circuits together. Alright, so as a quick recap, what are circuits? Circuits are devices that convert electrical energy into other forms of energy. They're loops of metal, typically, that provide a path from the negative terminal of battery to the positive terminal, or as we'd prefer to say, high concentration of electrons, high voltage to low voltage, low concentration. Alright, so when we have a complete circuit, say this operation game, and we say have touched our tweezers to metal, we've completed the circuit. There's now a path from the negative plate of a battery to the positive plate. Our electrons are going to flow through the circuit, and as they move, they're going to go through different devices. Our buzzer is going to convert some of the flowing electrons, or electric current, going to convert that into sound energy, and then our LED lights are going to convert some of the kinetic energy of those electrons moving into light energy, photons, right? Okay, and so circuits are set up in one of two configurations, series or parallel. And let's take a look at those, because it's important to start with these two, because more complex circuits will add these together to form compound circuits. All right, but our houses are parallel circuits, and our operation games that we're building in class are series circuits. Okay, and so the pros and cons are pretty straightforward. Series circuit, we can see that all the components are placed one after the next, right? Okay, and the downside of a series circuit is that, say we have, connected our battery through a series circuit, and then something happens such that our first light bulb breaks. Well, if there's a break in the circuit's no longer closed. That means that electrons can't flow, and so each of these light bulbs will turn off if one of them breaks, because there's only one loop, right? Parallel circuits are a little bit more robust in the sense that you have multiple loops, right? We can see one loop here, one loop here, one loop here. All right, and so if our first light bulb breaks, well, there's still two loops for our electrons to flow. Okay, and so most, you look at your cell phone, you look at your computer, it's not going to be just a series circuit or just a parallel circuit. It'll be a combination of the two. But since we like to make predictions in physics and do the odd calculation, one of the most important aspects of circuits is looking at electric current, because electric current is the kinetic energy of electrons moving, and energy is our universal method of accounting in physics, right? Whenever we see a change occur, energy is gone from one form to the next. All right, so looking at series circuits, the analogy we like to use, like all circuits, is water. If we say have a motor, our motor is a little bit harder for electrons to move through than a wire. And so if we take our water analogy, we use our battery as our pump, right? It's trying to force water through our conductors. And so when the water or the electrons get to our motor, it acts as sort of a choke point. It's got more resistance than the wires themselves. And so it's a little bit harder for water to flow through it. And say, what if we were to add up multiple motors in series, right? We can see just based on this diagram that if each motor acts as like a choke point by adding resistance to a circuit, then, if you just compare these two with just a single motor versus three motors, the total resistance has gone up, right? In the case of the three motor situation, right? There's quite literally less pipe or less wire with the standard thickness, the standard resistance, right? And so if we want to say calculate the current through a circuit with components in series, we're going to apply Ohm's law. Current is equal to voltage, electrical pressure divided by resistance. Okay, but what is the total resistance here? Well, we can just see that each one of these three motors has a compounding effect, right? So the total resistance we just add up. So say these are all 2 ohms, 2 ohms, 2 ohms. Our battery is 12 volts. That would be 2 ohms plus 2 ohms plus 2 ohms. That's 6 ohms over 12 volts. We get 2 amps. Okay, simple as it. Let's do some practice problems, guys. So for series circuits, we know that, of course, the total resistance increases just by adding the components up. It's kind of like pinching a pipe multiple times. And so if you add components one after the next, the resistance should just increase overall. So for question 1 and 2, go ahead and give it an attempt. What is the total resistance of the circuits to the right? All right. So for this one, we have R1 plus R2 plus R3, and we get 10 plus 15 plus 7. All right, that ends up being 32 ohms overall. We can therefore redraw our overall circuit as if there were only one resistor total of 32 ohms. All right, this one down here, we see we have R1 plus R2 plus R3 plus R4 plus R5. Our total resistance is therefore 25 plus 7 plus 32 plus 10 plus 3, which equals 52 plus 25, 77. We could therefore redraw our entire circuit as just one resistor of 77 ohms. And then we can apply Ohm's law. Current is caused by voltage and limited by resistance to find the total current overall. All right, let's move on to that. All right, parallel circuits, again, a little bit different. What happens to resistance in parallel circuits is almost a little bit counterintuitive, but let's just take a look at it. So again, same analogy. Our water and our motors, our battery acts as a pump for electrons, or in this case, we're talking about a pump, so water being pushed by a pump. Okay, and so our motors providing, again, our resistance, our choke point, narrower pipe. Okay, and so now we add a second motor in parallel to the first one. And even though they have the same resistance, we'll say 2 ohms again, notice how we went from one narrow pipe to 2 narrow pipes, right? According to the battery then, or the pump, it's now easier for electrons to flow. There's less resistance overall than there was before, because there's 2 narrow pipes for the water to go through, or the electrons to move through, than before. There's only one before, right? Interesting. So when you add components in parallel, the overall resistance goes down for the entire circuit. But let's just do a quick calculation. All right, say we have a 6 volt battery, and we have 2 ohm resistors. We'd say our total resistance, if we use this equation right here, is equal to 1 over R1 plus 1 over R2. And that becomes 1 over 2 plus 1 over 2. Well, 1 half plus 1 half is 1, so we get 1 over 1, and that's equal to 1. So our total resistance is 1 ohm, whereas previously each one of the motors was 2 ohms. All right, so that kind of makes sense, right? It's easier for water to flow with more components in parallel than before, because there's more thin pipes than before. All right? So we calculate current. Current is equal to voltage over resistance, and so we get 6 volts over 1 ohm, and we get 6 amps. All right? Simple as that. All right, time for some practice time, guys, on parallel circuits. So on these, we know that our total resistance of components that are placed in parallel, the total resistance should decrease as you add multiple pathways for electrons to flow. So our equation is 1 over R1 plus 1 over R2 plus 1 over R3 plus however many resistors you have overall that have been added in parallel. So go ahead and try the few problems on your own. We'll wait a second for you to do that. Go ahead and pause the video. Okay, so we just plug in 1 over 3 plus 1 over 3 plus 1 over, this one should be 3, okay, we get a total of 1 over 3 over 3. Notice how I did not just add up the denominator. We have to make sure that fractions have the same denominator before we can add the fractions together. Okay, we notice that some of us were having a hard time with that. That gives us a overall circuit that could be drawn like this, as it is exactly the same, equivalent to a simple circuit like this with one resistor, our total of 1 ohm overall. Okay. All right, question 2, what's the total resistance of the circuit to the right? Well, we have a little bit different. So we have this R0 term plus R1 plus this whole part right here in parallel. Okay, and then another part down here in series. So we'll say plus R4. And then this term right here is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And that we said was equal to 1 ohm overall. So we have R0 plus 1 ohm plus R4, and therefore our total is equal to 20 plus 1 plus 10, and we get 31 ohms overall, which we can draw as a simplified circuit that is just like this. R1 equals 31 ohms. Not too bad. Let's move on. Okay, so we've looked at combining resistors in series and in parallel, and we even had an example problem where we had one that had series and parallel within one circuit. And that brings us to nodal analysis, which is one of the best tools we have in looking at circuits. Why? Well, as we said in the past, current is caused by voltage and limited by resistance. And we know, of course, that as you put electric current through anything, you get thermal energy as a result. And so if we can know how much electrical current is going through any given component, then we can know how much electrical energy it's gotten, and therefore how bright it will be or how fast it will move. Okay, so if we know the voltage drop across any portion of our circuit, we can get that current. Okay, so nodal analysis is just treating voltage as electrical pressure. The idea being that every single node, every single wire, as shown here, has a different electrical pressure, a different voltage. And by convention, we choose one component, one node, to be our reference or our ground node, because just like speed in physics and even time, voltage is a concept that is relative, right? And so we say, okay, well, the voltage at this spot A is maybe 9 volts based on our battery. That's 9 volts relative to the voltage here at C, which is maybe 0 volts. Right? If it's our ground, then it should be 0 volts. And then we have a different voltage here at, we'll call this node B. Okay? But once we have the voltage at different nodes, then we can find out what the current is by applying Ohm's law, and we can find the current across any component. All right, let's do tiny practice just so we're familiar with it. This is something that is, a little above and beyond. Certainly, if you're a homeowner thinking about electronics, you don't really need node analysis. Parallel and series circuits is what is really all you need. But this is a good one for those of us who might be interested in looking at engineering in the future. This is how engineers talk about circuits. Okay? So practice time, label the voltages at each of the nodes in the circuits below. All right, so we want to find the voltage here and the voltage here. All right, we want to find the voltage here, and the voltage here, and the voltage here. All right, then we want to find the voltage at this node, and then the voltage at this node. Okay, step 1 is we'll do the first one together, set a ground node that all voltages are made relative to. All right, so we're going to say this voltage is equal to 0 volts. Then we have up here, if this is 0, then this node right here, connected to the positive terminal of our battery, it'll have the same pressure as the positive terminal of the battery. This one must be 9 volts. Okay, down here we do the same thing. Convention is our negative terminal of the battery is going to be our ground, so we'll say that's 0 volts. This terminal must have the same electrical pressure as the positive terminal of the battery, so we're going to say that is equal to 6 volts. And that just leaves us this guy here. And the question is, how can we find that one there? Well, for this one, we have to apply Ohm's law. And in particular, what we're looking at is we have a change in voltage causes a current and is limited by resistance. So if we know what the change in voltage is here, we should get a certain current and a certain resistance. We can find out what the overall current is through this circuit, and then we can use that to find out this missing voltage right here. Okay, so our overall current is going to be equal to the total voltage divided by the total resistance, which in this case is 20 ohms, and our total voltage is 6. So we have 6 divided by 20, which is 0.3 amps. Okay, this equation ends up becoming V, we'll call this A, VA minus VB is equal to the current going through the entire thing times the resistance of 1. Therefore, VB equals VA minus I times R1, and we get 6 volts minus 0.3 times 10, which is 3 volts overall. So our missing voltage here is 3 volts. All right. This would allow us to, if we had a more complex circuit, give us some more interesting results. That said, this particular circuit right here is one of the most famous circuits in electronics. It's called the voltage divider. Okay, one last one here. Go ahead and label the voltage as A and the voltage as B. All right, A should have the same pressure as the top terminal of our battery, and B is our ground voltage. It's connected to the negative terminal of our battery. It should be 0. All right, not too bad. Overall, what we've seen this time is we have series components and parallel circuits. Right? If we place components in series, the total resistance increases, and if we place components in parallel, the total resistance will decrease. And we have a fancy way of looking at this, which is called nodal analysis, which is an insight into how our engineers look at circuits. All right, see you guys next time.